Let's wait for another minute to see if anyone else joins. Okay, I think we can start now. Uh, just give me a minute. Okay. So, hi, good evening, everyone. My name is Umair Hussain, and I'm a PhD scholar in the Department of Mechanical Engineering, IIT Madras. And I welcome you all to the second out session of the course Finite Element Method, Variational Methods to Computer Programming. So, I think there are a couple of there are few new members this joining this week. So I would first start by my introduction. So as I told earlier, I am a PhD scholar under the PMRF fellowship at IIT Madras, and my work is related to computational material modeling. So I am working closely with finite element method to solve the chemomechanical coupling in the lithium-ion batteries. So I would like to know more about the participants that are joining. So if someone would like to introduce themselves, who did not join last week, so please go ahead. I hope my audio and the screen is visible, right? Can someone confirm first?
Yes.
Okay, thank you.
I have a question. Anyhow, I was present last time also.
Yes.
My question is regarding assignment one and assignment two. I have some doubts. I hope I you can clarify those.
Okay. So has the submission due date passed for both the assignments?
No, no, it is tomorrow.
So I don't think
No, no,
it will
I
be.
don't want the solution. I think there is some doubt in the question itself. Do you have
Okay.
assignment two?
Let me check. Just give me a minute. Week 2, right? Who is week 2? Yes, it's here.
It's here. Okay. The first page itself, where we have this last part in Rayleigh-Ritz method, we can approximate the solution as.
Mm-hmm.
Then in the last place, it is given like integral 2 to 5, 4x to the power 6 plus px5 plus 49x4 dx into C1. Now this LHS we are getting, but the coefficient is not C1, it is C square, C1 square.
Is it?
Can I answer this?
Yeah, sure. Go ahead.
I don't think so. You're doing something wrong. If you follow the procedure that was suggested Nandi sir, it will be C1 only. It will
It will be
be
C1.
only C1 only, nothing else.
Okay.
Because
Then
we don't have to vary this C1. Only there is variation in phi one and phi naught.
phi 1 and phi naught, that is correct only, but somehow when you do dv by
See,
dx,
ma'am, wait. If you go for that A UN phi I is equal to L phi I. That's right.
correct.
That way you can solve it. We don't have to vary this C1. C1 doesn't come in the square terms.
C1, okay, so maybe I was multiplying C1 then because
Please
dv
try
by
it
dx
once.
and
Please try it once again. You'll get it, ma'am.
fine, okay, okay.
Sure. Okay.
Okay, all right. But I don't think it's it's right to discuss assignments here. If it would have been some doubts about understanding the question, it's fine. But Anyways, yeah, would anyone like to introduce themselves? Anyone new candidate?
Good evening, sir.
Yes, sir.
I am Tamil Chandran. I am working in the area of flow-induced vibration, the vibration field. I am
Okay.
from Palakkad, Kerala.
Okay. So, are you a student or faculty there?
Actually, I am Dr. Tamil Chandran. I am working in the institute. It's called the Fluid Control Research Institute.
Okay. Nice. Very good.
So I thought
So,
I can learn something about FEM. That's why I thought I have joined this course.
so you had any experience with FEM before?
Yeah, I have worked in FEM softwares, this ANSYS.
Okay.
So
Nice.
that, but I want to know the fundamentals.
Right. Right.
That's
So,
why I have joined this one. Yes.
that's the issue with these softwares actually. So they work like a black box.
Yeah, yes.
You can define the problem to them, and they can generate some colorful plots for you. But
Yeah,
uh,
yes.
the beauty of FEM lies in what we'll discuss here. Okay, thank
Hi,
you, sir.
sir.
Hello, sir.
I'm professor at Bennett University.
Which university, sir?
Bennett, Times of India Group University.
Okay, sir. Nice.
And I've worked in industries also like NL Bangalore, IIT Kanpur. In I've worked at Altran India and MP Motors as an FE engineer. So right now I'm focusing on to teaching the students FEM. So I will to learn this.
Okay, nice.
Okay, thank you, sir.
So you all have had nice, good experience.
Yeah, I have. I have. I'm trying for resolve system also. If I secure that, I'll move on.
Oh, sure. Nice. Good luck with that.
Thank you, sir. Thank you.
Okay, then. Is there anyone else who would like to introduce themselves, or shall we move forward then? Okay. So today we'll briefly discuss week two's content, whatever has been discussed in the video lectures, and then we'll move on to the uh, problems discussion part. So last week we started with the variational methods. We understood what a minimization problem is, and how a minimization problem can be is an equivalence to the strong form or the differential equation, and that the same is equivalent to a weak form or the variational statement. So these three things are. I'll quickly summarize this. What we studied was that a minimization problem can be converted into a strong form using Euler-Lagrange equation, right? And a strong form can be converted into weak form using weighted residual statement, or as you can call it. And how do we go back from weak form to minimization problem? Can someone answer this? Anyone? Any guess?
If AUV, sir,
Yes, sir.
if AUV is bilinear and symmetric, and
Exactly.
LV is linear,
Yes,
it is,
yes.
then we can go for minimization problem.
Is
And the
bilinear.
problem solution is half into AYY minus LB.
Yes. Then YU is half A
AUV,
U.
UU minus LB.
Yeah, that's same thing. You either you write U or B. Right, exactly. So yeah, that is the way. These all are different representation of the same problem. So that's what we learned, how to represent in different ways. So now this week we moved on to the main topic that we are interested in. That is the finite element method. So we start with the 1D FEM. So the basic steps involved in FEM, whatever the problem is, the type of problem is quite it's similar to similar for every case. So we first start with discretization. So as you know, as you all know that in FEM the solution is a discrete solution. So let's say we have system, some solution yx having some random graph. So in FEM, what we do is we break it into elements and try to approximate the solution between each element. So if we are assuming linear approximation, our solution should go between these, like this and like this. That's case of linear approximation. If you are taking quadratic approximation, you will see we will get closer to the to the exact solution. And there are two ways to get closer to the exact solution. That is, one, we increase the order of approximation, and second is if we reduce the size of these elements. So then after discretization, so basically we break down our domain into number of elements. So say this is element 1, this is element 2, this is element 3. And after breaking into elements, we solve we get the algebraic equation for each element. And these equations are achieved using our weak form, weighted residual statement, or the variational form. So after that, what we do is we maintaining the continuity of each element, we assemble the element level equations to the global level. Uh, Finally, that gives our final system of equations, which is equal to the number of nodes in the system, the number of nodes in the system. And after getting our system of equations, we apply boundary conditions because there are more unknowns than the number of equation we will see. And after applying boundary condition, we get a system of reduced matrix or reduced equations, which we can finally easily solve. After that, there's post processing of the result. So if we want the result at specific points, or we want their derivatives, or even higher order derivatives, that is possible. So we started with the system of a discrete problem, that is a spring system. So here we have a system of two springs connected, and we want to find the displacement at each node. So first we discretize the domain. We break the system into two elements of two elements having different spring constants. Now next step is to uh, next step is to get the element level equations for each element. So here we do a simple balance of force. So there are two at each node in an element. So each element will have two nodes, and at each node there are two forces. First is the force due to elongation in the spring, that is the Fs, and second is the force from the neighboring elements. So if we sum up these forces, we'll get to achieve the equilibrium, to satisfy the equilibrium. We sum up the forces, and we get one equation at each node. So if we combine these two equations, we can get two equations in terms of the each nodal displacement. Similarly, we can do the same thing for second element. We'll get two system of equations. I mean, for each case, we'll get two equations each, and when we are combining it, we have two elements. So we have two elements connected at this one single node. Here we have a connection. So to maintain that connection, that is maintain the continuity in the displacement, we will keeping that in mind, we'll do the assembly, and finally we our total four equations would be reduced into three equations. So at junction we'll have a continuous displacement. So whatever the displacement we are getting here should be equal to here. This should be same. And another thing that we need to ensure at the junction is that the balance of forces. So the force contribution here should be add up. So now we are finally what we get is three equations, but you'll see that here the three u's are the unknown, uh, and plus we have one external force term also F, that is an unknown. So what we need is an extra condition, that is the boundary condition. Uh, so unless this one of the displacement is specified, this problem remains ill posed. So there will be many infinitely many solutions possible for this particular system of equations. So that is why we need a boundary condition. If we specify that, we are good to solve these equations to get a unique solution. So how to apply boundary condition is if we know one of the displacement, say u1 is known in this case, we can reduce the matrix. So if we write these equations individually, our second or third equation would be reduced like this in this way, and we can easily solve for the two unknowns u2 and u3, and later we can also solve for f here. Okay, so that is basically a simple procedure of 1D FEM, that is with an example of a discrete system. So next thing we studied was the numerical integration. So I hope till here it was clear. If there's any doubt, you can please stop me. So next is the numerical integration, and in numerical integration we specifically focus on Gauss quadrature rule. So in FEM, i- first thing is that the expression that we get, it's not very trivial to integrate them every time, and second thing is we usually work with a program, with a code. So in code we mainly rely on numerical integration. So we need certain direct formulae for solving particular some there, because in FEM you see there are many integral statements in getting the element level equation. So in order to solve those integrals, we need a numerical integration scheme. And Gauss quadrature rule is one of the most used numerical integration scheme. There's one more also, Newton-Cotes rule, but that is as far as I know, that is very rarely used in most of the FEM softwares. I think Gauss quadrature is one of the most used integration numerical integration scheme. So, the one thing that is important in this Gauss integration is that the formula is valid between the integration limit of -1 to +1, and that you'll see that is also crucial in for FEM also, because most of the domain we consider we transform the domain into this particular range only. So to solve any integral given integral, we transform it to the integration limit of the Gauss quadrature rule, uh, and then there's a simple formula. So there are Gauss quadrature points defined, and so these are derived Gauss points and their corresponding weights. So if we use this formula directly, we can solve any integration. So one thing so certain important features in Gauss quadrature rule is that first is that these Gauss quadrature points are not same as the nodes of the elements. So uh, in Newton-Cotes rule, as I remember, it is same as the nodes. It can be same as the nodes, but in Gauss quadrature they are never same as the nodes. And the points are also unequally spaced, and the integral limit, as I told earlier, it should be between -1 to +1. So the number of points that are required depends on what kind of function we are going to integrate. If it's a relatively simpler function, uh, then
Can I ask you one question, sir?
yes, sir, please.
If you have a four-noded element
Yes.
and we introduce a reduced integration element that is Gauss points, including that, we say that it has a contribution from one node. How do we say that? Which node is that?
Sorry, can
If
you
we have
repeat?
four-noded element
Yes.
and we say that we have a reduced integration element,
Okay.
that is S4R, or we can say in terms of ANSYS, it is uh, C3D8R in terms of solid elements. Then how do we say that? Which point is that that incorporates the contribution from all the four nodes or all the eight nodes?
Mm, so you're saying that in a four noded element,
Yes, sir.
uh, in a four node element, if there is uh, we are given certain number of Gauss points, you're
Yes, sir.
saying which Gauss point represent which node, right?
Yeah.
So
Contribution from, we say that suppose that I have four nodes,
yes.
so the contribution will be there from only one node. That's why we say that it's a reduced integration element.
Okay, okay, okay,
If you go for abacus convention or ANSYS convention, we get this.
okay, okay.
And when do we say that? That's what I want to know.
That I'll have to look into this because this
What about
particular.
integration points? So they are telling the integration points. What is that?
So integration points are actually Gauss points only. So if in a four node elements, if we have if we have some coordinate element like this that I've drawn here,
Mm-hmm.
so these are nodes. So integration point would be somewhere inside. You're taking say four
Oh
points
yeah.
only. They are actually somewhat inside the domain.
Okay.
Like if yeah, if in case if we talk about 1D case, we have two nodes here.
Yes, sir.
In case of one point, it's just here. If it's a 2 point, then it's right here.
Okay, sir.
Okay, so yeah,
Okay, sir.
I look into this. I don't have much about idea about this reduce element thing. I'll take a look and we can discuss
Okay.
next week maybe.
Thank you, sir. Thank you.
Okay. So yeah, depending on the type of function that we are going to integrate, we can find the number of we can determine the number of points, and the higher the number of points are, the more accurate result we'll get in terms of integration. So this is actually the formula to determine. So the number of points. R is the number of points, and P is the order of polynomial. So in terms of if we are talking about polynomials, then we can get as exact solution as possible. But if it's other than a polynomial, then they're bound to have some errors. Okay, so this is about Gauss quadrature rule. Then we have yeah, sorry about that. So then we have an example. We had an example of the continuous system. So we were given a different. Yes, sir. Did you raise your hand? Okay. So we're given a differential equation, a second order differential equation with the boundary conditions. Now, how do we use FEM for that? So first thing is that we in FEM we go from a strong form to the weak form. That is the variational statement that is written here. The next thing is we discretize. We have an element of size L, and we break into sorry, we have domain of length L. We break it into two elements of length L by 2, L by 2, say. And the next thing is we have to map the element from whatever given coordinate system to the standard the uh, this is called master domain actually. So we talk in terms of zeta, which varies from -1 to +1. So whatever the coordinates of the nodes would be, we map those coordinates to the zeta system, that is a master domain system. So this is useful in two ways in FEM. Firstly, as we discussed before, the Gauss quadrature rule works between this in this domain only. And the second thing is that if we transform into this domain, the calculation for each element would turn out to be almost same, except for the Jacobian that we can calculate for each element separately. Apart from that, every other step in getting the element level equation would be almost similar for each element. So, so we are given some standard approximation function for each element. I think these functions are not been have not been derived in the lectures. We'll see if we can do that if we get time. And so the solution for each element would be given by the summation of these approximation function multiplied by uh, the the nodal value of the solution for that element. And in the same way, the mapping function can also be derived like this. So so now if we assume the our discrete solution as this njuje, and we replace the weight function with ni, our variational statement becomes this. So these I and j actually represent the number of nodes. So if we look at this term, this is a matrix, a second order matrix or a second order tensor, and this is the vector of displacement, and this is the right hand side vector. So if for case of 1D linear elements, we get a 2 by 2 matrix and two nodal displacement, and right hand side we have two force term, and we write the boundary force term contribution separately. And ultimately for so again we have two elements connected at one node. Finally, when we'll assemble the element two elements, we'll have a global system of equations corresponding to three nodes. And at the node that is connected, we have a continuity in displacement. So u2 from element 1 would be equal to u1, sorry, u1 from element 2. And again the force term would be added. So we studied first this thing for the linear shape functions or the linear 1D element. Then later we studied this for quadratic element. So in quadratic element, we have three nodes per element, and uh, to so we define the shape function as a quadratic function, second order function, and to define second order function, we need three nodes. Again, the procedure, everything is same. The mapping function is now has three, since we have three shape functions, we have three terms here, and same for the solution approximation. Finally, for each element, we'll have a 3 by 3 matrix this time, because I and j would vary from 1 to 3. And now this time, since we have one element having three nodes, second element having three nodes. Now we'll have a global system of equation with corresponding to five nodes, and where the continuity would be satisfied at this node. So yes, that is how we'll get the equations for a continuous problem in an FEM. And we studied the case of two types of approximation, linear and quadratic. Finally, the applying boundary condition, and that part we have discussed. So this is it for the session for week 2. So if there's any doubt, we can discuss it now, or we can start discussing the problems.
Discuss the problem, sir. I think so better.
Okay, thank you. Okay, so we given a mm, minimization statement. Right, simplify and write it here. So how do we go about? So first thing is we have to derive the Euler-Lagrange equation for this problem. Not derive the Euler-Lagrange equation. We have to find the Euler-Lagrange equation. This is y prime square minus 8y. Okay, so how do we? What is the formula for Euler-Lagrange equation? Can someone tell me?
Del f by del y minus d by dx of del f by del y dash.
Exactly.
Yes, sir.
So del f by del y will give. So this is actually the function f, right? So del f by del y will give us minus 8 and del f by del y prime will give us to the power 4, sorry 2, then we'll have minus 8 minus 8x cube dy by dx. I hope this is what we get, right? I hope I did right. So what we'll get in the end,
Excuse me, the screen is not visible.
sorry, uh,
The screen is not visible.
It is visible. It's visible, I think so.
can you check
So,
the connection, please?
somehow I'm not able to see what she's writing.
Can you see the screen moving now?
Yes, working.
Yes, it's okay now. Yeah, working. Okay.
Okay, fine. So finally we get an equation of this type: x cube dy by dx plus 1 equals to 0. I hope this is correct, right? Okay, so this is our Euler-Lagrange equation. How do we get the variational statement?
V into that of the complete differential equation. So
Exactly.
we have to do partial derivative first.
Sorry, it's 2 to 5. So I think in this case we don't need to do integration by parts.
Yeah, yeah, you're right.
So I think this is the variation statement that we can get. There's one more way to get the variation statement directly from the minimization, the functional, if you can recall it. Yes. So you can just write off del pi equals to 0. This is called variational operator.
Yes.
So if we apply it on our, so I hope I'm doing it correct. So, so how do we send this in? Send this variational operator inside?
So we have to take A and B, A and L. Am I right?
Okay, so the first term, do we apply chain rule?
Yes, sir.
Q- I'm not sure if x would be considered a variable for this operator.
It will not be considered variable. So we have to directly consider delta or B, whatever you can say.
So it's like 2 dy by dx into delta y minus 8 delta y. I don't think this is exactly what we got above. This can be written as v. This part, I don't know if we're missing something here or. Anyways, that's fine. We got the basic statement above. Just trying to experiment if this would work here. Okay, so next is use relay rates method to solve for y. So we're given functions y equals c1 p1 plus p naught, and p1 is also given. So what should be phi naught here?
Sir, 2 into. If you have a one, you are not specified the boundary conditions.
Uh, isn't it? Isn't the boundary condition
Essential boundary
specified?
conditions will be specified, no? Am I right?
Sorry.
It has to satisfy the essential boundary condition. Then only you can consider the P naught.
Yes, exactly. So we need to specify the essential boundary condition. Mhm.
It was something y
Yeah, yeah.
x equal to 2 is equal to 2 and y x equal to 5 is equal to 5.
Yes, yes. So we know the integral limits here. So the variation at the x equals to 2 and x equal to 5 would be equal to 0.
Then we have the y naught as 2 by 5, 2 by 3, 5 minus x plus 5 by 3, x minus 2 as P
Can
naught.
phi, you're saying that phi not x is, can you repeat, sir?
If we have the essential boundary condition as y x is equal to 2 is equal to 2 and y x equal to 5 is equal to 5, then our P naught will be 2
Yeah,
by
but
3.
why would that be?
It was given as per the problem that you're solving now.
Okay, it was given there.
Yeah,
So, mean y at 2 equals to 2 and y at 5 equals to
5.
5.
Yeah.
So phi naught shouldn't be equals to x, isn't it?
That will not be satisfying the both the conditions. No, we cannot specify x. No, am I
Uh,
I
right?
think it is correct. It will satisfy both the conditions
so if we'll put x
because
equals to 2, phi naught becomes 2. Yeah, and
correct.
if we put x equals 5, 5 phi naught becomes 5. isn't it?
How will it? I don't think so. It's not correct.
So this is phi naught. I'm saying phi naught
No,
equals.
we have to consider both essential conditions, and then only we can distribute that.
Yeah, so I am considering both essential condition. Yes, you told me that the boundary condition given was
Yeah,
y at y at x equals to 2 equals to 2, and y at x equals to 5 equals to 5. Isn't it a
sir.
linear relation, right?
So this cannot be done by this way, no? You have to say the un as per the un. You have to decide that, no?
You're saying that you mean yn.
Yeah, that's right.
So in related method, we choose phi naught in such a way that it satisfy the given boundary condition, and phi one should specify the homogeneous version of the given boundary condition.
As per the
So you'll see at
lecture, as per
x
the lecture,
equal.
it was said that.
Sorry.
As per the lecture, it was said that you have to consider both the boundary conditions, and then only you can decide that.
Yeah, you have to consider both boundary condition for phi naught.
Yeah,
But phi one should be chosen in such a way that whenever we have say x equals to 2 here, phi one would be 0, and whenever x equals to 5 is x equals to 5, then phi one would also again be 0. So so phi one wouldn't contribute in choosing in satisfying the boundary condition for phi naught, isn't it? So right now the function that I am writing here, phi naught equals to x, doesn't it specify both the boundary condition, this and this? Don't you
I
think?
don't think so. It's correct.
So you see, sir, if phi in phi naught, if phi naught equals to x, if I write phi naught at x equals to 2, what would I get?
If we have this p1 x equal to x minus 2 x minus 5,
Uh-huh.
then both has to satisfy the essential boundary conditions. Then phi naught x should be u1 into x2 minus x by x2 minus x1 plus u2 into x minus x1 by x2 minus x1.
2.
These both 5 and 2 should be considered while considering our phi naught x.
Can
Because
you repeat? I couldn't get it.
if you see the lecture,
So
it
you're
was
saying
given
that
that we will
uh,
consider both the boundary conditions while considering the phi naught x.
yes, that is what I am saying. I am also considering both the
We
both
cannot
the.
consider this phi naught x as x directly.
So isn't it it isn't it satisfying both the boundary? So these are the
No.
two boundary conditions, right? Am I right?
Yeah, yeah.
These are the two boundary condition. So
Mhm.
tell me if I write phi naught equals to x, what would be the value of phi naught at x equals to 2?
2,
2, isn't it? And what would be the value of phi naught at x equals to 5?
5.
In that sense, if we can put that, phi one x will be 0 then.
Why would 5 1x would be 5
So
1x would be 0
5,
at the boundary points at x equals to 2 and x equals to 5, right? That is given here.
Hmm.
5 1. So if whenever we are assuming a solution in Rayleigh Ritz method,
Yes, sir.
we have one function which is not multiplied by any constant, and we
Yes,
have
sir.
several other functions which are multiplied by constant. These functions should satisfy the homogeneous version of the boundary conditions, and this should specify this alone should specify the given boundary condition.
Essential boundary condition. Huh?
Yes, essential boundary condition, right? In case of related method, I don't think we need to ensure the natural boundary condition because they automatically come in
No,
that equation.
natural boundary condition is not considered. This phi one x also has to satisfy the essential boundary condition.
Yes, it also has to satisfy the essential boundary condition, but the homogeneous form of this essential boundary condition. So
Okay.
phi 1 at x equals to 2 should give 0, and phi 1 at x equals to 5 should give 0. And that is how they have, in the question, they have already defined phi 1 here.
Okay, sir. Okay, let's
Okay.
proceed.
Yes, sir. So we can choose phi naught equals to x, right? Here, and so so now we can assume y equals to c1 into x minus 2 into x minus 5 plus x, and if we write dy by dx, that is equals to x square c1 to 2x minus 7 is plus 1. Let's check if this is right. And v, when we assume v as equals to phi 1. So we have x cube times dy by dx. That makes it c1 into 2x to the power 4 minus 7x cube plus x cube plus 1. So we are going to get a big expression here. C1 into x square x plus 10
Then
2x to the power 4 minus 7x cube. So so this is going to be a very lengthy integral. We can save some time and assume that we can solve it on at this point, right? So we'll get one term, some number times c1 here plus some other number equals to 0. So we can get c1 from this equation. Okay, so I hope this was okay. So this is how we can use the Riddle-Ritz method to solve for, sorry, to solve for the given problem. Okay, so we'll again start with some basic problem. So since we started working with FEM, first thing we do in FEM is get the weak form. So how do we do that for this? So how do we proceed to get the weak form? Anyone?
we need to go to
Yes,
variation of differential equation,
exactly.
and this is del square k nabla u plus minus f x. Yeah.
So we assume any 2D domain omega. And next thing is, what is the next step here?
So we have to do a partial integration.
We do integration by parts.
Yeah, yeah.
So
First,
does,
we need to expand that
yeah,
nabla.
yeah, we can just distribute this. No, we don't need to expand that. That's the beauty of doing integration by parts.
Okay, so
Minus So it's only the first term that we do integration by parts. So the basic trick in doing integration by parts is we shift this derivative operator here. So we
Okay.
write the integral term that we get is with a minus sign, gradient of p dot kappa times gradient of u, and then we have a boundary term. So we assume the domain omega has a surface gamma, and then we have the second term. We don't write this del operator. Just write k del u times a normal dotted with normal vector. Then we have minus v time fx d omega equals 0. So this is our weak form. So this here is our bilinear term. It is symmetric also here, and this is a linear term. So that's how we get the weak form for any 2D, 3D system of equation. Okay, so yeah, this is in this exercise we'll try to derive the approximation function or the shape function that we call uh, for any random element. So we given an element here x equals to 0.2 to x equals to 0.5. So how do we do that? Does anyone have any hint? So we are trying to find a linear approximation function. So how can we approximate u, the solution at this element? It is a linear function, some linear function, a plus bx. And is there any other way we can define uh, the the solution u for this element?
In natural coordinate systems, or we can say in global coordinate systems and in local coordinate systems.
No, I'm not talking about the local and global. In general, we have some element.
So we can
For
take a reference of point that is origin,
okay,
and then we can place x at a distance from that origin.
hmm,
Am I right?
I'm not talking about transforming the coordinate system.
Yeah, yeah.
I'm talking about what representation do we use for the approximation of solution. So uh, you remember we write solution like this u1 n1 plus u2 n2 in
Shape
terms
function.
of the shape function, the approximation function.
Yes.
And since it's linear, we have two approximation function, and we can also assume it to be a linear function a plus bx. That is both way we can assume it. So now how do we need to derive this and the n1 and n2. So we'll try to do that. So when x equals to 0.2, what what is the property of the approximation functions?
N1 plus N2 is equal to 1.
Yes. And what
And at
else?
point 1, it will be at 1.1, it will be having N1 is equal to 1 and N2 is equal to 0.
Yes, yes. So at x equals to 0.2, we'll just have u1 left on the right hand side. N1 will be 1, n2 equals 0. And on left hand side, we'll have a plus 0.2b. Okay, and at x equals to 0.5, we'll have on right side we'll have,
N2 is equal to 1 and N2 is equal to 0. N1 is equal to 0.
yes, so we'll have just u2 left, a plus 0.5. So we'll subtract these two equation. We'll be left with u1 minus u2 equals minus 0.3b. So we'll get b equals to u2 minus u1 0.3, and we'll substitute this back to equation 1. We'll have
Okay.
a equals to u1 minus 2 by 3 of u2 minus u1. That gives 5 by 3 of u1 minus 2 by 3 of u2, or 5 u1 minus 2 u2 by 3, isn't it?
So,
So if we substitute this back into our equation 1, so sorry, we have u1 n1 plus u2 n2, and this would be equals to a is 5 u1 minus 2 u2 by 3 plus b is u2 minus u1 upon 0.3 times x. So this is the equation that we get. Now using this equation, can you guess how do we get our n1 and n2? Any guesses?
you have to put the value of x equal to zero point 0.2 and then proceed.
If we put
And
x equals to 0.2, then
and
uh,
similarly, we have to put the second equation will be zero point 0.5. We'll get the two equations and u1, u2, and then we can solve it.
okay. So if we'll put x equals to 0.2, we'll get 5 u1 minus 2 u2 by 3 plus 2 u2 minus 2 u1 by 3, and that gives us
First equation.
5 u1 minus 2 u1 would be 3 u1 minus 2 u2 plus 2 u2 becomes
So it will be, I
0.
think, 7 un. 7 u. Okay. So
We'll get
yeah.
u1 plus n1 equals to u2 plus n2 equals to u1. I think we'll get back to our original equation 1, isn't it?
Uh,
So since we've used this condition already, I don't think this will using this again into this equation would help us. So the thing is that we just have one equation and we need to find two things. So what we can do is we have a left hand side arranged in a way of u1 n1 plus u2 n2.
so we can have a property n1 plus n2 is equal to 1.
Mm,
We
okay,
can use that property n1 plus n2 is equal to 1, and then we can deduce that.
okay. So if we'll do that, we'll have on left hand side we'll have u1 n1, and this will be u2 1 minus n2. So sorry, 1 minus n1 plus u2 minus u2 n1. So again, if you see that u2 and u1 are also unknown. If
Yes,
we
sir.
write approximation function, u2 and u1 should not be part of that. So one similar, so simple thing is, what if we can arrange the right hand side in this same way? U1 times, we have multiple u1 terms. If we combine all the coefficient of u1 together, what we'll get? We'll get
Yes,
5
yes, yes, you can get it. Yeah.
5 by 3 minus this would be 10x by 3, right? Plus, and then for u2 also, we'll have minus 2 by 3 plus 10x by 3. So in this way,
These are the two C functions, I think so.
yes, yes, exactly. I'll write them clearer. U1, and this is, try to write in terms of the nodes, the nodal coordinate values, zero point 0.5 on zero point 0.3 plus u2 times x minus zero point 0.2 upon zero point 0.3. This 0.3 is nothing but the length of the element, zero point 0.5 minus zero point 0.2. So there's, you'll see, this is our n1, this is our n2.
Yes.
So you'll see there's a general trend to write n1, n1 and n2. So that is, when we write n1, we write xb minus x upon xb minus xa, and n2 is x minus xa upon xb minus xa. So this is your general formula for, if you would have, instead of writing zero point 0.5 and zero point 0.2, if we would done this way, we would have got these general formula. This is the general formula for 1D linear elements. That's the
Yes.
approximation function for the 1D linear elements. And if you will go to the natural coordinate system, put xa equals to minus 1 and x b equals to plus 1, what will you get? Xa will be minus 1 and xb equals to plus 1. So in that case, n1 would be 1 minus x by, so x will be 2, and n2 would be x plus x plus 1 upon 2, 1 plus x upon 2. If you remember, if I'll just uh, what if I just write this theta in place of x, right? If you remember the approximation function that we used in class, these were the approximation function, isn't it?
Yes, yes.
So that's how we derive the approximation function for any type of element. This would, if you will see, this would work for even for quadratic or higher order elements, and this would work. This technique would even work for 2D elements. What you have to do is, you have to, so if you're in case of quadratic, you have a plus bx plus cx square will be equals to u1 n1 plus u2 n2 plus 3 and 3. And if you write for you'll have three coordinates in this case: x equals to x a, x equals to x b, x equals to x c. You'll get three equations. So those three equations would be some matrix 3 by 3 times a b c. This would be equals to u1 u2 u3. So you need to take the inverse of this matrix this side, and you need to find basically ABC. And then if you can get ABC, you can write the in terms of U1, U2, U3, you can arrange the equation to look like this equation, and there you can get N1 into N3. But the kick in this approach is that the Jacobian should be invertible. The determinant of the Jacobian should not be equal to 0. And you'll appreciate this thing more in 2D elements. In 2D elements, if we have some triangular elements, uh, we cannot have a zero area triangle. That would give us a non-invertible matrix. Can't have 2D element like this. So that's why these elements, even very high aspect ratio triangles are not preferred in FEM. So that is way to get the approximation function. So I think we'll see more about this in when we'll go for 2D FEM. Anyway, I just had this in mind, so I discussed this.
Sir, what is Jacobian? What do you mean by that?
Uh,
Actually, it's a shape deviation from actual shape. Am I right?
Sorry,
Jacobian.
I said Jacobian. I think I meant determinant.
Okay.
Yeah, I said right. It should be invertible, isn't it? Then I said Jacobian should not be equal to 0.
So in terms of elemental, it is said that it is an out of plane deviation from actual shape.
Sorry,
Deviation from the actual shape.
actual what?
Shape.
Okay. Oh, okay. Sorry.
Suppose that it is a rectangle, it has some deviations from
Yes,
that
yes, yes.
rectangularity, then it can say a Jacobian is there.
Yes, yes, yes. Jacobian basically, but here in this case, I didn't mean to say Jacobian. I actually meant to say determinant should not be equal to
Okay, sir.
0.
Thank you. Sir. Thank you.
No problem. Okay, so now we have this given differential equation. So we have uh, shape functions calculated in the previous problem. So for the element in previous problem, calculate the elemental stiffness matrix and post vector for the differential equation. This. So first, for if we have a differential equation, first thing is we get the weak form. So the weak form of this problem would be we ignore the boundary term here. Okay, I'll just combine these two terms. Okay, so this would be our weak form. So for elemental, for the stiffness matrix, we need to calculate this term, and we assume B equals to Ni, U equals to Nj Uj. So we have N1 equals to 0.5 minus 6. Okay, I'll write 5 minus 10x by 3, and N2 is 10x minus 2 by 3. Okay, so what would be the derivative of dn1 by, that would be minus 10 by 3, and dn2 by dx is 10 by 3. Okay, all right, so substitute this. So what should be we'll get a matrix like this. So what should be a K11? So K11 means V would be instead of V will have N1 and instead of U will have N2. So dV by dx would give us so dn1 by dx would be minus 10 by 3. So minus 10 by 3 square and plus v into u would be n1 times n1 because we're calculating k11. Okay, so we have 100 by 9. We have 25 minus plus 100x square minus okay 100x 19. So that is our integral. We have 125 minus 100x plus 100x square per 9. So you pretty much get the idea, right? We'll save some time and leave it here. So this can be calculated. We'll get k11. So how do we get k12? For ease of understanding.
So what is the formula to calculate this K11?
So yeah, I was going to explain that. I thought I made it unclear. So we substitute this v and u approximation in the above equation. We'll have 0.5 dni by dx dnj it would be dnj uj, but I can take uj out of because uj is not function of x plus ninj dx. So this whole term times uj equals to nix dx. So this actually is our kij k matrix.
Okay.
So if we'll have I equals to 1, j equals to 1, we'll get k11. That's how we did it. And if we want k12, we have to put I equals to 1, j equals to 2. So here we'll have minus 10 by 3 into 10 by 3. And then we have 5 minus 10x by 3 into 10x minus 2 by 3. You see how complicated this integral can get if we just use the direct the coordinate system of the given element. We did if we would have transformed it into the natural coordinate system, then it would the shape function are much prettier. Okay, so we can evaluate this also. And how about getting K21? Should we even worry about K21? Because we see that
They're
our
symmetric, I think so.
yeah, it's symmetric.
Yeah.
Exactly. So our Kij is symmetric. So K21 would be equal to K12. And again to get K22, we put I equals to 2 and j equals to 2. We'll have contribution from N2 for both V and U. Though in the same way we can calculate that also. how to get the force vector. Force vector is this term here. This will gives a Fi. So Fi will be Ni into x dx. So we have two terms here. I equals to 1. We have 0.2 to 0.5. 5 minus 10x by 3. So right, yeah, into x. So we can calculate this also. And F2 we have 0.2 to 0.5, 10x minus 2 by 3 into x, and we get this term. So that's how we get the force matrix. So sorry, force vector. Okay, so I hope this was clear here. Okay. So we have given coordinate system 2 to 6, and we want to transform it to our, sorry, so we have to transform it to our natural coordinate system. Zeta equals to -1 to zeta equals to +1. All right, so we since this is basically 1D linear approximation, sorry. So we have x equals to a plus b is I. So how do we go about it? So we know that at x equals to, sorry, 2, zeta equals to -1. So our equation becomes 2 equals to a minus b, and at x equals to 6, zeta equals to +1. 6 equals to a plus b. So if we add the equations, we have 8 equals to 2a. So we get a equals to 4, and then if we substitute back into the equation, we have b equals to 4 minus 2. We get 2. So our mapping function becomes 4 plus 2 zeta. If we want to take the Jacobian is this 2 in this case. So in case of a linear mapping, we have a constant Jacobian. Okay, so that's how we transform this coordinate. Now we have to find the mapping of domain 6 to 2 to a natural coordinate. So now we have our coordinate system is reversed. 6 to 2. Right? We have to map to zeta equals to -1 to zeta equals to +1. So again, we assume a linear function. So at x equals to 6, this time we have a minus zeta equals to -1. X equals to 2, we have zeta equals to +1. We add these two, we get 8 equals to 2a, a equals to 4, and this time b is 4 minus 6 minus 2. So our mapping function is a equals to 4 minus 2 zeta. So this time if we see that the Jacobian actually changes sign. Okay, so that's the difference between if we reverse our coordinate system. So our Jacobian becomes negative. So find the mapping function using shape functions for linear 1D element for the previous two problem. So we were given 2 to 6, right? X equals to 2, x equals to 6. So using shape function, what is the formula? We have this n1 times x1 plus n2 times x2. So n1 is 1 minus zeta by 2 and x1 is 2 plus n2 is 1 plus zeta by 2 into x2 is 6. So we have 1 minus zeta plus 3 plus 3 zeta. We have 4 plus 2 zeta. So we got this mapping function using our approximation function also, shape functions. So the term shape function is actually more relevant for this expression. This actually means that these functions are used to approximate the shape of the elements. This is not so much evident in the case of 1D elements, but in 2D uh, 2D case, the case of 2D elements, uh, are, are the shape of the elements is very random. So these functions help us to map this random shape to the standard shape. That is so this term shape function is more relevant in that case. So anyway, if we have opposite domain x equals to 6 to x equals to 2, then we have again same formula 1 minus zeta by 2 into 6 plus 1 plus zeta by 2 into 2. We have 3 minus 3 zeta plus 1 plus zeta. We get 4 minus 2 zeta. That is same as we got before. So these are two ways to get the mapping function for the case of linear 1D elements. Okay, so here's a question for you. In FEM, as size of element tends to 0, the error tends to anyone to answer this?
Infinity, I think so.
So we'll check this. So we have this element. Now if I try to reduce the size of the element, say half. Right now this is the error. But if I want to reduce the size of the element and do a linear approximation, this error is reduced here. As we keep on uh, reducing the error, we get closer and closer. You see that our solution becomes more accurate. So the error tends to 0 here. Okay, all right. As the size of the element becomes less, our approximation becomes the same order of polynomial. For the same order of polynomial, the approximation becomes more accurate. So the error tends to 0.
Yeah, yeah, that's.
Okay, so we have a cost integration exercise now.
Um, mm,
So we have a function where we have a give integral minus 1 to 1 4x cube minus 3 dx. So what should be the value of r? I mean, how many Gauss points do we need? 1 to r. Sorry. Anyone? How many Gauss points should we use for to get a accurate solution?
So power is p plus 1, that is 7, 4, that is even. Then r is equal to p plus 1 by 2.
Yes. So we need two Gauss points, minimum two Gauss points, right? R equals to 1 by 2. So what are two Gauss points? Zeta 1 is, what was it? Minus 0.557577 something. Let me check. Yeah, plus minus 0.5773. And the weights are 1 for each point in this case. Okay, so we write 4 into minus 3, and this is multiplied by 1, plus we have 4 into minus 0.5773 cube minus 3, and weight again equals to. Okay, so if we try to solve this, we have, so this term and this term would have opposite sign, and weights are also same for these two. These two would cancel out. We'll be left with minus 3 and minus 3. That is, I think, minus 6 is the answer for this, hopefully. Now if we try to do with a lesser value of r, suppose we take r equals to 1, so our psi is 0 and weight is 2. So the integral is 4 into 0 cube minus 3 into 2. So even with this also we got a pretty much same answer. Can we try with a higher value of r? So I don't remember the formula. 0.774, 0 plus minus 0.774, and weights are 0.888, 0.55. Corresponding to this, W is 0.888 and point this for it is 0.555. So our integration becomes 4 into minus 0.774 cube minus 3 times 0.555 plus 4 into plus 0.774 cube minus 3 into 0.5, 4 into 0 minus cube minus 3 into 0.888. So again these two terms would cancel out. We'll have minus 6 times 0.555 and minus 3 times 0.888. One 1.11, I guess, plus 0. That would be approximately equals to 2 minus 3 into 1.998. It is almost equal to 6. So the error that we actually got here is because of the approximation of these weights. This is actually uh, some I think some root terms. These are actually are some root terms. So we did some decimal approximation for this. That's why we got some very little error here. So again, we got pretty much same answer if with the higher value of higher number of points. So now we have a non-polynomial function to integrate. So how do we go about that? So we'll start with for a r equals to 1, 2, and 3. We'll try with e in each of the three way, and we have. Sorry, this is supposed to be x square, I guess. So we have I equals to 1 to r. Okay, so we'll take r equals to 1. So our zeta I equals to 0 and wi equals to 2. So what is our integral? F of 0 into 2, that is e to the power 0 into 2. So that gives us 2. Okay. Now we try with r equals to 2. I equals to plus minus 0.5773 and wi is 1 each. I hope this is right. 0.5773, right? So our integral becomes e to the power minus 0.5773 square into 1 plus e to the power plus 0.5773 square into 1. So again these two terms would be equal. So minus sign would be squared. We'll have 2 times of to the power 0.5773. This is actually much different than the previous answer we got with r equals to 1. That was 2 into e to the power 0. This is 2 into e to the power 0.5773. I'll just calculate this in the calculator. If anyone can get the answer meanwhile, please let me know. So it's 0.5773 exponential. It's 2 into 2. Sorry, just a minute. So it's wrong. It's actually the value of E. So it's 0.5773. 1.7812. This multiplied by 2 is 3.562. I'll also write one more place. Okay, so there's a bigger gap now between the solution from one integration point to the to two integration points. So we'll try with three integration points. One was 0, and other one was 774. This was 0.888. So we have I equals to so we have 0.8 e to the power 0 plus 0.55 e to the power minus 0.774 square, plus we have 0.55 e to the power again we have 0.88 plus these two terms would be same, 2 into 0.555 e to the power 0.774 square. I think I forgot one thing in previous problem. There should be a square. I think the answer was wrong here. Let me check. 0.5773. The squared is 0.33327 and exponential of this is 1.39. Please correct me if you see me doing anything wrong. 5 5 and that is multiplied by 2 is 2.791. Okay, this is the correct answer. Now for this case we have 0.774 squared is 0.599 and the exponential of this is 1.8204 and multiplied by 2 we get 3 point, this thing is 3.64087 plus we have 0.888, so we get 4.5297. Okay, so we get this solution for 3 points. So we see as we increase the number of points, the value of the integral is increasing, and if we keep on increasing the point, we'll get a more accurate solution. But since it's a non-polynomial integral, then we will never get exact solution as in case of polynomials. So I hope this was clear. We still have some time. This is the end of the problem. If there are any doubts, we can discuss them now.
Master, can you help me a little bit about how to execute this Gaussian quadrature?
Sorry?
In, can you help me a little bit about how to use this Gaussian quadrature
Yes.
in solving the Rayleigh integral?
In solving the Rayleigh integral. Oh, that's
E
interesting.
to a, there is a term over there that is very difficult to solve. That is e to a minus I k r by r.
E to the power minus kr by r.
I k r by r.
Okay. I kr is in the complex
K is the, yeah,
part.
yeah, yeah, you're right, sir.
Okay. I don't know if we can really use it for complex integrals.
K is the wave number. It's I've completed a
Yes.
PhD on this only.
Okay. Nice.
So I wanted to implement this Gaussian quadrature. I've already implemented, but I'm not clear about that.
It's actually e to the power minus I k.
R
Yeah. And
by R.
by r is here.
R is the distance from the source point to the sound propagating point.
Okay. So this integral is between which limits?
So we can uh, we can take it from 0 to 2 pi.
Okay.
It is a spherical domain. We can say that
Okay.
we have to convert that into a spherical domain. So generally, what do we do? We remove this R as constant. Then only it is solvable. The bottom R.
Okay.
We take
Uh,
out this. Yeah,
we take this out as a constant.
yeah, yeah, yeah. Generally, it's assumed on the
Okay.
basis of some of the, and there is a term over there, velocity also multiplied in between.
Okay. So I think
I'll need your help later on, but
sure, sure.
proceed. Sir. Okay.
Yeah, yeah. Anytime. I'll also try to see if this actually works.
So it will be by dr by r
Sorry.
minus I k r by r.
Here,
Yeah,
right?
yeah, you're right.
So this R is the
And that this is not d theta, it is ds,
okay.
and the limits will be 0 to a, 0 to b. The suppose that I am using a plate.
Okay.
Two limits will be 0 to b. Yeah.
Okay. So we'll need to get the variable straight here. So if it's a surface integral
Yeah, you're right, sir.
and okay.
Generally, we do the quad. It was
Mhm.
someone do the direct integration approach, and most of the people have done the numerical integration approach.
Yes, yes. I think we what we need to straighten up here is the mapping to our natural coordinate
Yes, sir.
domain.
Yes, sir. That was what the problem I was facing.
Okay, that's interesting actually. Anyways, this is completely new for me also. So,
Yes, sir. Yes, sir. So,
apart from FEM, we've never looked into Gauss quadrature in other things.
sure, sir. Okay. Thank you.
If there doubts, if anyone wants to ask any doubts, we can discuss them now
Yes.
regarding whatever the week's content was and whatever I have solved here so far.
So suppose that I have submitted the assignments, both our assignments.
Yes, sir.
When will the evaluation be done? Suppose tomorrow is the last date, 9th.
Yes, yes. I think as after a few days, the solution comes up on the website, and I think by that time you'll have the answers of the evaluation of the assignments ready.
Suppose that tomorrow is the last date, then we'll get that by 9 or 10. I think so, right? Or 10.
I'm not too sure. Personally, I haven't taken any NPTEL course before, so I don't have much idea about this. But yeah, you can expect this within next week.
Sure.
It
Thank
will
you.
come soon. And earlier, sir, you had asked about reduce integration or reduce element.
Reduce integration points.
Okay.
Generally, we say that suppose that we don't use Gauss points. Okay.
Uh-huh.
In that case, you have to use complete elements, all the nodes. Consideration of all the nodes are considered. But when we use this C3D8R or S4R, then we have to consider the Gauss points or integration points only.
Okay, okay, okay. What I can recall is basically we reduce in reduce integration we reduce the number of Gauss points.
So
That
it,
is
already it will reduce the number of Gauss points. Now, if we have four noded elements,
uh-huh.
so it will have a contribution from one of the integration points.
Okay, okay. So you're saying that that means basically we can get the integral for a four node element using just one point, isn't it?
Yeah,
Yeah, yeah, yeah. So that basically helps us. So in this case, what the catch is here is that for a four noded element where four nodes are there, only contribution for one point is enough to get the integral, isn't it?
it has some demerits also. This there is a term called R glassing. You might have heard this.
What is this called? Can you
R glassing.
R glassing?
HOU R glassing.
Okay, yeah, yeah, I think I have heard this.
So this
Basically,
R glassing occurs when we use the C3 data elements. So in that case, we have to if we are getting this R glassing, that is zigzag behavior in the distortion or deflection.
okay, okay,
In that case, we have to go for different elements, that is incompatible mode elements.
okay, that's interesting.
Or you can some we can enhance the stiffness of the structure or element. Then you can remove this R glassing.
Okay, okay, that's interesting. I
Thank you.
haven't had much experience using FEM with more structural problems.
So that's why if I combine my knowledge with the FEM and this theory, then I think so it will be marvelous, and I can explore myself to industries too.
Yeah, right, right, exactly. You because you have already had some industrial experience.
Already, I have simulated more than 800 models. What I am doing now is Python scripting of my all the models and everything. So this is what you might have heard. This I've also taken the class of this Bandhopadhyay sir from IT Kanpur.
Okay, for which course?
You met abacus. He was teaching abacus there.
Okay, so you've had experience with Abacus before.
Yeah, yeah, more abacus and both ANSYS also.
Okay, okay. I have personally actually never used in my work. I have never used these commercial softwares. My my in my work I mainly rely on open source solvers. So I use one FM library called Deal2. If you've heard its name,
Pardon, sir? Can you
Deal
repeat?
Deal2.
Okay,
So it's spelled like DEAL and this two.
okay, deal two.
So it's more fundamental programming basically. We write simple C++ code. As you would have in this course, the instructor has shown the MATLAB code.
MATLAB. Yeah.
So in the same way, we write a basic program in C++. But these GIL2 libraries have very good classes and objects which support this the solvers. There are very good functions there. So a lot of things can be automated directly done, like imposing boundary condition and
Okay.
assembling the local the elemental equations to global equations, all that thing.
Nothing.
But it's very fundamental. Like you have to write a solver from scratch. You have to write a proper C++ program for that. So
Okay. It
so
completely works on C++.
yes, yes.
Great, sir. I'll explore this. I think
Yeah, yeah.
so.
If you have time,
Hmm.
please look at that too. So that will actually help your understanding of the subject also.
Yeah, sure, sure, sure. I'll do that.
So, anyone else, if have any doubts, you feel free to ask. Now we have some time.
Good evening,
Sir?
sir.
Yes.
So myself, Dr. Amandeepa,
Hello.
and I have recently joined this course few days back.
Yes.
So this is my first meeting that I am attending the online.
Okay.
Uh, so actually, I am from mathematics background,
All right. All right. Yes.
uh, and I am working in the field of theory of elasticity, thermoelasticity, basically.
Okay. Nice.
And I want to learn FEM basically for solving. Actually, at present, I am using these analytical techniques to solve my problems, no, mathematical
Yes.
problems.
Okay.
So my aim is for learning FEM is basically for validation purposes.
Okay. 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 Yeah, that's
Yeah,
interesting.
yeah. So my first question is, because I have seen the FEM courses, they are run by civil engineering departments, mechanical departments. There are so many courses I have seen on the list now. So
Yes.
is this the correct course which I have joined? My first question is this one.
Okay. Okay. That's interesting question. Actually.
Yeah, because I'm confused which course I have to, because I've seen so many courses run by different departments. One is by civil also.
Okay. Okay.
I've
Uh,
seen your contents, variational methods to computer programming. I am very much familiar with calculus of variations and numerical analysis and all that. That's why I have joined this one.
Okay, okay, yeah, yeah. If you have fundamental with this, I think if you're from mathematics background,
Yeah,
it's much familiar for you.
yeah.
Variational method and these Taylor-Ritz method, weighted residual method. I hope if you can catch this, then this is a good course for you. Because the good thing about this course is that it takes you to computer programming also.
Yeah, my aim is to learn a Becker software basically. I have seen the sir is working recently to which you are talking. He's working on Beckers. He might be helpful for us also.
Okay, yeah, yeah, yeah. It's nice if we can form a community here
Yeah.
where we can help each other. So it's wonderful. So, as
So
sir
I,
mentioned, he did some course on abacus also. That some you met.
huh? Yes, sir.
Sir said some course he
Yes,
did
yes, yes. But he's talking.
abacus.
Na?
So you can work on. You can install the software and start working, ma'am.
So
Maybe your
can uh,
mechanical department do have that.
no, I am having the software.
Mm-hmm.
So can you please help me to how to basically first I want to learn that software, na?
Ma'am, it's a straight flow process.
Okay,
First, you have to make a domain,
okay,
then assign the metal properties,
okay,
mesh it, and go for step like static general and everything, and then you can execute. You
okay,
can
sir.
validate all your models, any of the models that you
Yes,
want,
sir. Yes, sir.
by using mathematical relationship.
So to learn abacus, so one of my teacher, he's in mechanical. He suggested me to first learn FEM, so that I become aware with at least the
Yeah, yeah, yeah,
terminologies and all
yeah.
that. This will be
These
helpful.
softwares do have a different variations in
Yeah.
terms of Lamech constants.
Yes, sir.
But I think if your goal is to straight away use abacus
No, no,
and
I want to learn also because I want to solve my both.
okay, yeah,
Because through FEM to learn
Without
abacus is a proper job.
uh,
Yeah,
must say, without learning this FEM, we
FEM.
are just dull. Abacus and these softwares are just, I think so.
Right,
They're
right.
just scrap
Yes,
if
sir.
you
Yes.
don't know the basics.
That's right. That's right.
Hmm.
But I was thinking that there are more simpler course also on FEM.
Which
Uh, Last year also I took this doubt session for this course called Basics of Finite Element Analysis, Part 1 and 2. It has two parts.
okay, sir.
So that is that is taught by Professor Nachiketa Tiwari from IIT Kanpur.
Yeah. Hmm.
It's a very fundamental course actually. But my complaint for that course is it's too fundamental actually. If you want to go fast and cover up a lot of things in FEM, you have to go with two courses actually. But this course here covers pretty much most of the FEM, most of the fundamentals of FEM without going much into deep.
That's why I joined this because
Yeah,
Nachiketa Theory sir's class I have attended that before.
yeah. It is actually very good if someone is very new to all this. He doesn't know
Yeah,
much about
I
maths and
know.
all.
You're right.
That course is very good.
Hmm.
So
But
I don't have any background. I'm not familiar with FEM.
okay, it's fine. I think this course would be good for you. I
Okay,
hope.
sir. So should I also listen to the lectures, basic courses of FEM, which you are telling?
I don't think you would need that much because you
Okay.
have a fundamental in mathematics.
Yes, sir.
Most even the first part of that course, most of the starting portion we spent on the
Mathematics.
analytical method.
Okay.
The different numerical methods to solve PDs, relay rates, and all those.
But I feel that sir, something is missing. Uh, like sir Maiti sir or someone, he taught directly the shape functions. He told
Yeah,
something.
yeah. That is the thing. That is why I specifically spent some time on deriving the approximation functions.
So if person don't know what is shape function, then he will not able to
Yes,
map it
yes,
on anything.
yes. That is correct. And I also got some ideas about this thing from that course with my experience with that course.
Yes, yes, sir. It was
Yes,
quite interesting. This variational method was quite interesting. I was missing that only, and that I determined that I have to learn this, and now I'm well versed with it. I think so. I
yes.
can capture.
Actually, there's a lot of things in FEM. I personally, in my during my PhD, I have done two courses in FEM, and every time I take a course, I find something new, and there are some different ways to look into things.
That's what
But
I was thinking that some if I repeat one course to other, there is some
yeah,
variations. So that's
yes,
what sometimes get confused.
yeah, and every time there will be things that you won't be able to make sense how this thing is working, how this thing becomes this. Like that when we are applying the in the when we take the weak form, we have that Neumann boundary term. We have that
Yeah.
boundary term coming up. So we consider the weight function to be zero wherever the discrete boundary condition is specified. And I had done by that time I had done two courses in FEM, and I had no idea why this so. Then later I did a variational course in my college. So there I understood that the variation is actually equals to zero. That's why the weight function is
Oh.
supposed to be zero there.
So what about this? They are telling about two boundary conditions: essential and natural.
Normal. Yes.
Okay.
Yes.
There is a third boundary condition that is mixed.
Yes.
So when do we use that?
I have never come across any such problem where we had to use it.
The problem
But
that
it's
I'm telling you
basically
that that's using mixed.
okay. So I think that that's basically a combination of Dirichlet and as well as natural boundary condition, right?
Yeah.
So it's like using a Dirichlet boundary condition to get the natural boundary condition, or vice versa, something like that. I have never personally used it, so I don't have much idea about it. But it's something of that kind. I'll look into this,
Okay.
and
Okay.
maybe
Sir.
we can discuss it next time.
Sure. Sure. Thank you. Sir.
I'll write it
Shall
here.
I leave then?
Okay, sir. Yeah. If anyone is having no doubts, then we can
Thank you.
close
Sir,
it. Yes, sir.
sir,
Please go ahead.
how can we access your doubt clear section video, sir?
In the page of the course,
Ah,
here you have on the left side course outline.
okay,
So there you have week 1, week 2, week 3, and
okay,
at the end there is a section of problem solving session July 2023. Can you see
okay.
that?
Ah, yeah, yeah.
If
Problem
you
solving. Yeah.
click there, you'll get to a page where there will be a link to a Google Sheet.
Okay, okay.
On the Google Sheet, I upload the YouTube link of the videos and even the Drive link if you in case you
Yeah,
want to copy.
I am able to see your first week lecture. Okay,
Yeah, yeah, yeah. So
okay. Thank you, sir.
we upload there.
Okay, thank you.
Okay. So
So you are taking only the tutorials? I mean to say the lecture is by someone else?
yes, ma'am. Yes, ma'am. So the courses are run by the professors at
Yeah.
various IITs, and so we are PhD scholars. We have to take. We're supposed to take the doubt session.
You are the PhD scholars under the sir?
No, not under sir. So
Uh,
I am a PMRF scholar,
okay.
and as part of PMRF, we have to uh, perform certain deliverables. We have to teach outside our institute. So
Okay.
NPTEL has provided us this platform to uh, give our time into this, and in return we get to complete our teaching hours.
Okay, sir.
Right. So, anyways, if you have started working with FEM, anytime if you have any problem with FEM understanding anything, you can contact me. My there's a section for ask a question also. You can post your doubts there, or you have my email address.
What's your email address, sir?
Uh, I'll just type in the chat box.
Okay, so you will be dealing with all our doubts sessions.
Yeah, yeah.
Okay, so sir will not be available.
Sir, I don't know if he'll be
Okay.
available. If you
Okay,
can
okay.
try to reach him, but
Okay.
these are actually rerun courses.
Okay, rerun courses. Oh, sir is already up. The videos are already uploaded. Done.
Yes, 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 yes.
Okay, okay.
Course is actually
I
not live.
understand. At present, sir is not available.
Yeah,
This is
yeah.
what. Okay, sir. Okay, sir. Thank you. Nice to.
Okay, no problem. Thank you, ma'am. I'll conclude the session now and end the meeting. Okay, thank you.